In this video we'll be verifying identities. In the previous video we used trig identities to solve trig equations, simplify trig expressions, etc. But in this video we'll be doing what is called verifying identities. So basically sometimes it's called proving identities. So we'll have one trig expression set equal to another, so we'll have an equation and we are just going to work through one side and make it look like the other side to verify it or prove that it's equal. So we have some notes here about the differences. For example, we have cosine x equals 1. Well, that's only true for certain values of x, whereas this one right here is an identity, cosine x, secant x equals 1, because no matter what angles we plug in here for x, it always equals 1. So that's the difference. And this is conditional upon what x is for it to be true. This, it doesn't matter what angle we plug in, it's always going to be equal to 1. So let's look at this first example here. It says, how do you verify or prove an identity? Start with one side, transform it step by step until you arrive at the expression on the other side. So they have this example worked out for you. So the general rule of thumb is start with the more complicated side. So we have 1 and we have cosine x secant x. Well, cosine x secant x is definitely the most complicated. So we start breaking that down, and just like last time, what they're doing here, they're rewriting secant x in terms of cosine x, so they get this. And then you have cosine x over 1 times 1 over cosine x, which becomes cosine x over cosine x, which becomes 1. So you have verified. You made this side look like this side. You simplified it down until it matched. So you verified or proved that cosine x secant x does in fact equal 1. That's what your goal is here. Some tips here. Start with the more complicated side. We discussed that. It's often better to write in terms of sine and cosine. We discussed that in the last video when we were working with identities. So we want to transform them, make substitutions, simplify fractions, combine terms, etc. to simplify. Remember all of our identities, the reciprocal and the Pythagorean and the quotient identities from last time. And especially the Pythagoreans, just realize they can be written in many different forms. So these are all forms of sine squared x plus cosine squared x equals 1. These are all forms of this identity right here, and these are forms of this identity here. So let's go through those quickly. This right here is just the identity rearranged. This is the 1 minus cosine squared x. That's the difference of two squares right here. This is the difference of two squares, so this is it factored, how it would look. And same thing here, difference of two squares right here, and this is how that would factor. So you need to be looking out for all of those different forms and realize that you can work with them in any of those forms. Alright, now to an example. Prove the following identities mathematically. So we want to prove that secant x minus cosine x is in fact equal to sine x tan x. Now this is considered the most complicated side because we have a subtraction as opposed to a multiply. So we're going to be working with this side to make it look like this one. So secant x minus cosine x. They tell you here, use a reciprocal property to write secant x as a fraction, and it's also going to rewrite it in terms of sine and or cosine, in this case in terms of cosine. Find a common denominator. So in this step right here, we have two fractions that we're subtracting, so we need a common denominator. So we'll multiply both sides by cosine x over cosine x. Here, I should say the numerator and denominator by cosine x over cosine x. That way right here, this multiply gives us the same common denominator there. So 1 over cosine x stays the same, minus cosine squared x over cosine x. So cosine x times cosine x here gave us this. 1 times cosine x gave us this. So now we have two fractions subtracted with a common denominator. So now we'll smash it together as one fraction. So that's going to be our numerator right there, 1 minus cosine squared x. And we have smashed that together all over our common denominator, cosine x. Use a Pythagorean identity. 1 minus cosine squared x is the main Pythagorean identity rearranged. So that's going to equal sine squared x over cosine x. So let's go through that quickly. The identity starts this way: sine squared x plus cosine squared x equals 1. That's just, this is it rearranged. We just moved the cosine squared x over to this side and made it equal to sine squared x. So that's where we go from here to here. Alright, and then we're going to split this into two pieces. So we'll make it sine x over 1 times sine x over cosine x. Realize these are equivalent. Sine x times sine x is this sine squared x. 1 times cosine x is this cosine x. And then remember, our whole goal was to make it look like this right here. So this is sine x over 1, sine x over cosine x. That use our quotient identity, and that is tan x. So now we have it set equal to, we have proven that it equals the right hand side to begin with, so we are done. That would be our final answer there. So the answer here is the work that it takes to get to this place. Alright, another example here. Cosine x plus sine x tan x equals secant x. We want to verify that all of this does in fact equal secant x. Obviously the left side is the most complicated, so that's the one that we're going to work with first. So first we'll start by rewriting everything in terms of sine and cosine, so that's always a good idea. Cosine x plus sine x times sine x over cosine x. That's tan x. That's our quotient identity. And now we can just simplify this a little farther. So we get cosine x plus sine squared x over cosine x. That's just multiplying this together. Now we want a common denominator, so we're going to multiply this piece by cosine x over cosine x. Realize originally it was over 1 like this, so then we get cosine squared x plus sine squared x. They're both over a cosine x because we established that common denominator here. It was already the denominator here. So now let's smash it together as one fraction there. So we get cosine squared x plus sine squared x all over cosine x. Okay, and this is the Pythagorean identity that says cosine squared x plus sine squared x is 1. So next step we get 1 over cosine x, and that is equal to secant x. So we're done. We have proven that all of this does in fact equal secant x. So the answer here is all of this work right here to get us to this point. And that's it for this example. Let's do one more. Alright, next example here. Cosine theta over 1 minus sine theta. We need to show that that's equal to secant theta plus tan theta. It could be debatable here which one is more complex, but we're going to say that this one's more complex because you have a fraction and you have a subtraction in that denominator. So we are going to make that side look like this side. So they give us a little hint here. Multiply numerator and denominator by 1 plus sine theta. So we'll do that. Cosine theta over 1 minus sine theta, and multiply that by 1 plus sine theta over 1 plus sine theta. That's always okay to do because that's equal to 1. This is a form of 1. So then we would get, distribute in here, and we would get cosine theta plus cosine theta sine theta. And then in the denominator we're going to have two factors basically, 1 minus sine theta times 1 plus sine theta. This is, if you FOIL this out, you're going to get 1 minus sine squared theta, because this is the difference of two squares factored here. We have square root of 1 is 1, square root of sine squared theta is sine theta. We're adding them in one parenthesis, subtracting them in the other. This is the difference of two squares pattern factored. So next we're going to make it after it's been FOILed out. So let's do that next. The numerator we're leaving the same. So again, if you FOIL all of this out, you're going to get 1 minus sine squared theta. Alright, so we have a subtraction still here in the denominator. We want to try to get rid of that, so that's what we're about to do. Cosine theta plus cosine theta sine theta. Alright, And then the 1 minus sine squared theta is the main Pythagorean identity rearranged. That's equal to cosine squared theta. Remember, the original identity is this. Cosine squared theta equals 1. So all we did is we subtracted the sine squared theta to the other side and got this, which is going to be equivalent to this, cosine squared theta. Now we can, I'm going to go ahead and split this into two pieces. We're looking here at what we want to end with. Okay, so I'm going to split it into two pieces like this is two pieces. So cosine theta over cosine squared theta plus cosine theta sine theta all over cosine squared theta. All I did is I took the numerator and basically split it down the middle. Now you have to leave it over the denominator of cosine squared theta. In previous problems we've gone from this and smashed it together as 1. Well, here we're doing the opposite. We're separating it. So if we work through this, we get cosine theta over cosine squared theta. Well, that is going to cancel with one of these, so I need a placeholder of 1 left on top. So 1 over, and all we have left in the denominator there is cosine theta. Here, this cosine squared theta goes with one of those, so I'm left with plus sine theta over cosine theta here. 1 over cosine theta is secant theta. That's one of our reciprocal identities. Plus sine theta over cosine theta is one of our quotient identities, and that's equal to tangent theta. And now we have shown that we have worked it down until it looks like the other side. So we are done, and again the answer is all the work that was required to get to this point. When you're verifying or proving identities, there is often more than one path to take, and if you start down one path and it's not getting you anywhere, then you just back up and you can start over or start from one of the steps in your process until you get to where you need to go. But just realize there's often more than one path to get you the work you need to prove it. That's it for this video.